kilocos and read have already, so the cloud has become a droplet. So we have got the water from the cloud. So, but okay, so these are the two different computations that you can do on a total graph. So this was quite a motivating relationship for us to discuss, ask the question of oriented total coloring on oriented graphs. Okay, then going back to the slide. So what's the natural analog? How are we going to define the total coloring and total chromatic number for oriented graphs? But prior to that, we should know what oriented arc coloring is, because oriented vertex coloring and arc coloring put together will be the total coloring. And arc coloring is pretty, even though the equations looks pretty verbose, let's look at a picture which will speak volumes. An oriented coloring of G, if you want to do arc coloring of G, if you want to do, then you can do the vertex coloring of the line diagram of G, and then you are done with the arc coloring. So starting with the XYZW graph, with the intention of coloring the arcs, you name the arcs conveniently, distinctly, and then the second section of the graph says that the arcs are now extracted out of the graph. So now the arcs are going to play the role of vertices, and then the adjacency, the incidence of the arcs, namely E1 and E2, the underlying graphs are incident on X, right? So we have an arc from E1 to E2, similarly from E1 to E3. So this is going to be the line digraph. Not a line digraph, it's actually line digraph, correct. Not the line graph, it's a line digraph. So now you color this. If I color this, I can easily say that 2 colors is sufficient, and I can now I can color the edges back in the original graph, because my E2s and E1, all my E's are colored now. So this way the arc coloring was very nicely translated into a vertex coloring problem. And there are 3 very good and very popular result in this paper, in this topic, namely given the acyclic chromatic number of a graph, they were able to bound the chromatic index of the oriented graphs. So this is a very interesting thing. Acyclic chromatic number simply says that if you color a graph with say whatever colors and take any 2 colors, take any pair of colors and look at the graph induced by this pair of colors, okay, there won't be any cycle in this. So that's such a chromatic number is called acyclic chromatic number, and that naturally will be more than the chromatic number. And if you a priori know the acyclic chromatic number, then this result by Ockham, Pinlow and Eric says that it is bounded above by 2k into k minus 1 plus the k by 2, and this cannot be improved. Everything has been done to this upper bound, nothing can be done more. And so you can ask, now that we have for if G is a planar graph, so acyclic chromatic number happens to be 5, while the chromatic number is 4, acyclic chromatic number is 5. So you can put 5 and then see that how much it comes to. 2 5s are 10, 4s are 40 minus 2, it will be 38. So it will be bounded over by 38 chromatic index. Plus, sorry, it's 42. Is it plus or minus? I think it should be minus, right? Is it plus? Is it right? Okay, whatever it is. If it is plus, it is the 42. If it is minus, it's 38. Okay. I think I made a mistake here, or maybe I'm correct. So now you have the result for the planar graph coloring, and you have got the result for the arc coloring. So both the techniques you can put together and test whether it works for total coloring. When we did that, and when we did that, we found that it actually worked. Grafting the 2 techniques, but you will get a very, very loose upper bound. I mean, while these upper bounds are pretty tight, the upper bound which we get something around 120 or so. So 42 plus 80 is 122, correct? So the planar graph is 80 and
we lose that flow, right?
Huh?
We lose that flow. We lose something. It's not this plus that.
Yes, this plus that, exactly. We are getting this plus that. 122 is the number. Otherwise, it should 160 or so it will be coming. So we bring it down to 122. It's a plus. I mean, so that using the inherent structure of the total graph, we should be able to find out better homomorphic images. So how it is done to be done? I mean, really, I have not thought in those lines. When you say that when you are in a hurry to cross the woods, you miss looking at the trees. So now I have already crossed the woods. Now I will traverse the woods again to look for the trees. And with regards to planar oriented graph, girth restricted, it's been very nicely shown to be less than equal to 4. So we take this work can be naturally, this question can be easily translated into oriented total coloring and ask the same question. And with regards to the degree bounded, well, finally, how do we actually define, in terms of homomorphism, how do we define the oriented total coloring? That needs to be vetted through first. Say for instance, you have a 2-die path, green, yellow, red triplet of vertices. We have some 4 kinds of relation, you see. We have a a vertex to edge, edge to arc to vertex, and vertex to vertex, and arc to arc. Kind of loosely speaking, we have 4 different proximity relationships, and then each of this relationship will need to be coloring friendly. So whenever they are approximate, you can't have the same colors. So that would mean that here this arc cannot be red color, because it will be red proximate to red, which coloring prohibits. So initially you have this 3-die path. What we can do is, the relationship between this vertex and arc can be distanced by putting a vertex between the red and the yellow. So this arc becomes a vertex. Similarly, this arc becomes this green vertex. So this way we are able to bring in a vertex-vertex relationship for every vertex arc and arc vertex relationship. Correct? So this is a traditional technique of subdivision of graphs. Take an edge, put a vertex in the middle. That's precisely what is done, and the arc flow is retained. Now what we are left with is, we have to depict this relationship, this proximity, and this proximity, while this is already there. See, in the process of putting this green vertex between this cyan and orange, yellow, in the process I have distanced it, but here they were adjacent. So in order to bring the adjacency, we can easily draw this arc and make them adjacent. So what we have done is, we have retained all the proximate relationships in this converted graph. And what is this? This is basically the square of the subdivided graph. And this is precisely the way even the total graph is defined for the undirected graphs. You take a subdivision and then you square it. Interestingly, the same definition applies even for the oriented graphs. And then the problem becomes now with the same homomorphism framework. We need to just ask this question, that do we have a proper image, homomorphic image, for the square of the subdivision graphs. Now we just have to do a vertex coloring. And to take a quick look at how the coloring happens, we see that there is a foci here, and all the colors have to be unique. So some easy problems have been addressed for the paths, forests, and the trees, for the cycles, and for here there is a mistake, that plus k by 2 is missing here. Plus k by 2 is, or
no, I think
I think we got rid of, huh?
That one is minus, and when we try to put that minus here,
Put that minus here, correct. So that should have been minus there, correct, correct. Now that explains. So we are not able to do the minus, so it becomes
so it's not this plus that.
that. Correct. Correct. Yeah, this explains the missing gap. And then for oriented cycle, depending on how the orientation is, we have an elaborate result. And for tournaments, if the tournament is acyclic, it is pretty obvious. I mean, it's just one line argument to say that you need 2n minus 1 vertices for total coloring, total oriented coloring. Now for the Pelli tournaments, we can ask this question. Pelli tournament is not acyclic, it has got cycles. So it's found that it is less equal to 2n minus 1, but do we really need 2n minus 1 vertices? Is it tight bound? I mean, this question is open. We were unable to solve this. And does any 2n minus 1, this is an interesting thing. People who are interested in looking at coloring aspect, specifically coloring aspect, will find this one pretty interesting. That you have a Pelli tournament on n vertices, and then you do a 2n minus 1 coloring. Do you get a colorful Hamiltonian path? That is, you have to find an oriented path, the directed path. It's a directed path on 2n minus 1 vertices and with distinct colors. For the smaller numbers like 7 and things like that, it works. For 11 also it works. On n vertices, correct. On n vertices. For smaller numbers, we have checked it works, but for larger numbers, does it really hold? Why would it be helpful? I don't know, but the path is really colorful. Maybe that's one motivation. So this is the discussion on the planar. The reason why we would be interested in trying to get this tight bound worked out is because the outer planar graphs, they have a tight homomorphic relationship with Pelli tournaments. So if you can color the Pelli tournaments well, then you can do the coloring of the oriented outer planar graphs also. So the complexity is the decision problem of OTC 7 with this, is NP complete. Well, can you do with 6? That's an open problem.
Also the upwards.
Upwards, correct. So upwards is what?
So from 7, we do not actually know what is for 8, 9 and so on.
No, but no, for 7 it's true, then 8, 9 also will be true, right?
It will be hard, but
Couldn't put the gadget, okay. Now, prior to going to this fractional, I would like to go to another interesting thing which interested me a little more, is the oriented chromatic polynomial. So the oriented chromatic polynomial is asking not to optimize the number of colors, but is asking you to give the total number of colorings you can get for a given set of colors. Suppose I take a graph of 4 vertices. I give you say 400 colors and ask you this question: how many ways you can color this 4 vertex graph? Plenty, right? It's a combinatorial problem. 4C1 into 4C2 into 4C3 into 4C4. Yes, nicely you get a huge combinatorial number. So that's the kind of question we are asking here. So how many different colorings you can get? We are not trying to optimize anything. So if you have the homomorphic polynomial is a specific application of this chromatic polynomial, which actually Birkhoff tried to use the chromatic polynomial to prove, give an analytical proof for the 4-color theorem. So from there these problems are motivated. And what is the way you can go about computing this homomorphic polynomial? So given a graph, how many different target graphs you can construct which can be colored with the given set of colors? So that would be the question. So you have to find out you have to have a mechanism to enumerate set of homomorphic images. So, given an input graph, and the moment you are able to get the homomorphic image, here homomorphic image will be minimal, correct? So, once you have such an image, you will know it is now the problem of getting the total number of colorings of the input graph translates to getting the total number of colorings of the homomorphic image graphs. So, the counting problem of the domain actually becomes a counting problem of the range, and the range incidentally is a very well governed graph whose structures are pretty known, because you are going to construct that homomorphic image. So, once we know that image, we know how to color this. Usually the image is an absolute clique, and when you have an absolute clique, you can convert it to a tournament, and then the tournaments are, and a number of tournaments you can get, and each tournament the number of ways you can color. So, the total sum will be the total number of colorings you can have for this oriented graphs. So, how do we go about reducing this graph? How do we construct these tournaments? Suppose if you have a simple 4 vertex graph as an input graph. Now, what we can do is if you want to color this, we can see that x and y can take the same color, right? Because they both are not connected, and then they are converging towards this vertex. So, x and y can take both red color, so to say. So, in which case there are cases, suppose I give you 4 colors and then say that you can color it the way you want. Then initially I will try to be stingy and trying to give minimum number of colors, and then I will relax the condition and try to use all the 4 colors. So, when I am stringent, actually I am coloring a graph which is something like this. I mean, x and y is taking the same color, and here x and y are taking different colors because they are being adjacent. In both these cases they are going to be adjacent, in which case they are going to take different colors, and this is the case where x and y are going to take same colors. So, when you are coloring a graph, there are options where 2 vertices may take the same color, may not take the same color, whichever way you approach. If you take the same color, it is as good as having the input graph with these 2 vertices merged, being identified rather. Or in case you are going to assign 2 different colors to this, then it is as good as having an arc between them, and the arc can be either way. So, from a given input graph G, we get 3 different versions of this graph. So, the problem of computing the oriented homomorphic polynomial for this graph amounts to computing the homomorphic polynomial of these 3 different graphs, and then polynomials can be added. So, this argument can be further brought down, and in the leaves you see they are all tournaments. So, the input graph, how many different tournament images you can construct for a given input graph, the problem just boils down to that. And then once you have a tournament, the polynomial of the tournament is known, and then you have to add the. So, we can ask the question of what is the homomorphic polynomial for an independent set. Every polynomial, every graph is actually we will see that if you can solve conclusively for the independent set problem, that for other graphs also they have to be algebraically equivalent. We suspect that there is some algebraic equivalence of this polynomial and the polynomial of any other graph. We have to just set it up because this is a superset of all the other polynomials. And what about the sign of the polynomial? The interesting question here is that whether they are alternating or not. Do we find any pattern? And how about the coefficients of the polynomial, of the powers? So, we have some primary results on this, and the alternating sign property has been established, but with regards to the relationship of these coefficients, namely the unimodality property, which says that this Cn minus 1, they keep increasing, their absolute value keeps increasing, reaches a maximum value, and then start decreasing to C1. Why it will be important is not a very good question at the right now, but can we actually prove such a Cn minus I which actually breaks this increasing and decreasing sequence, and unimodal because you have only one such a Cn minus y. This we are able to testify for a few graphs, so we leave it as a conjecture. So, this problem incidentally has been solved for the undirected graphs by I think Huch and Kuhn. Kunnanhook or Kunhook. There are two authors, right? Kunnanhook, yeah. Kunnanhook. And enumeration problem is I will just wind up with the one statement about the enumeration problem, because the problem that has been done here has been achieved using a computer program. So if we can have an analytical approach to arrive at a solution, at least a solution technique, that will be interesting. The thing is, planar graphs have an absolute click of size 15. You cannot have more than that. Now the question here is, how many clicks, planar clicks you have, planar absolute clicks you have, which are minimal. Minimal in the sense that if you remove even one arc from this graph, the graph is no more an absolute click. So in that sense, it is edge minimal, arc minimal. Now the question here is, can you get all the configurations? First thing, can you get a number? Even if you cannot get a conclusive number, can you enumerate the configurations? Do you have a technique to enumerate the configurations? So that problem was tried, and the technique that we adopted was exhaustively get all the planar graphs which are non-isomorphic using the naughty graph generator, get all the non-isomorphic graphs, and then try to find an orientation to check whether it is an oriented click, and having found that it is an oriented click, check whether it is minimal. So the minimality check is done using a database. Whenever you find a minimal click, you keep shoveling it in the database, and whenever you find a new click, you see whether it is isomorphic to the earlier generated click. By doing this way, the computer program was able to get this magic number 1, 2, 3 for easy to remember. So thank you. Now I leave the stage to the next speaker.